Hello, welcome everyone. Welcome to Zahid's Data Mining channel. Today I will be presenting one of our recent incremental learning algorithms. Let me share my screen. Okay, you can see the slides where I will be very briefly presenting an algorithm called adaptive decision forest, and it is an incremental machine learning algorithm. The paper was published with my wonderful colleague, Dr. J.R. Rahman. And this paper was published in Pattern Recognition, and we also have made this paper freely available on arXiv. That's a preprint version of the paper that you can freely download from there. And Pattern Recognition is a very top quality journal, which is Score 2020 rank A star, and also has a very high H-index of 245. And we have also made the code of this algorithm freely available. So if you go to my personal web page, if you just search me by Zahid Islam, you will eventually reach there, and go to publications and search for this paper, Adaptive Decision Forest. You will see the code is available, paper and the preprint version are also available. Now, if we click on the code, we can go to this repository where we will also see a manual there and a README file. And the manual will tell you the details and step-by-step details of how to actually download the code, install it in MOA, which is a platform where there are many other incremental learning algorithms are also available. And also, it also has a data set and batches of data there. So you can apply the code directly on this data to readily enjoy the coding, the program, the algorithm. And also the code you can see that is publicly available. So that is the case. So you can actually see this code there. Now, as you all know, incremental learning, in this case, we are considering batch incremental learning, where data keeps on coming in batches. So with time, you get more and more data. And if that is the case, then if you have first trained a model based on your first batch, then that model was good at that time for prediction purpose. But when new batch of data arrives, then you may need to adjust that model depending on the new information, new data that you have just received. Sometimes you may not need to adjust, but sometimes you may need to adjust. Or sometimes you may even need to create the model from the scratch. So this is what incremental learning is. And in that way, generally the idea is that you will not need to remember the old data as you keep getting new and new data, because then your data will be very big, data set size will be very big, and every time if you need to recreate a model from the scratch, then the complexity of the model building process can be huge. Now, this figure very briefly shows the main concept of our technique. To keep the videos simple and short, I may not explain everything in full details, but please feel free to read the paper. But very briefly speaking, what we do is we create a permanent forest and we create an active forest when we get the first batch of data. And these forests are, for example, random forest, SIS4, or forest PA, any forest algorithm. And a forest is an ensemble of trees, right? So we create a forest and we call it permanent forest, and we copy that and we call it active forest. That's batch one, first data when we get. So now if we have unlabeled data for which the class label is not known, then we can apply this active forest to predict the class label, and we can get the prediction or classification. Now, when we get the second batch of data, we repair the existing permanent forest. How we repair it, I will explain it in a very briefly though in a minute. And then we check whether the active forest is repairable or not. By repairable or not, we mean the the confidence level of the leaves of that forest. So there are many trees, right? And every tree has many leaves. So we check the confidence level of each leaf on the new batch data. And if the confidence level has significantly dropped compared to its confidence level on the original data, that is in this case batch 1 data, then we think that this leaf requires attention. And if the number of leaves or percentage of the number of leaves requiring attention is higher than a threshold, then we consider this tree is not repairable anymore. So we have to do something else. But if that threshold is low, I mean that number or that percentage is lower than the threshold, then we consider that tree is repairable, and then we repair it. The same way that we used to repair the permanent forest as well. Now, once we have the active forest and permanent forest and we have some unlabeled data, then we use the better of these two forests for prediction of that unlabeled data. Then here we go, we get the third batch. And let's say in this case, we again test, we first repair the permanent forest. Permanent forest is always repaired, right? As you can see here. So once we get the third batch, we test whether active forest is repairable or not. Here it says AF repairable. For this line, AF repairable. And when we see, no, AF is not repairable, then what we do, we create TF, temporary forest. We create another forest. So this temporary forest. And how we create temporary forest? We create temporary forest based on the window of data. So in our technique, we always remember a given number of batches, given number of most recent batches of data, and keep that in our window of data in case we need to build a temporary forest. So in this case, we have 3 batches of data. In the window size is 3, so we always keep 3 batches of data, and we used it to create the temporary forest. And again, when we have unlabeled data, we use the best of these 3 forests. Now, when we get the 4th batch, batch number 4, then we again check whether the active forest is repairable. Let's say in this case, no, it's not repairable. Is the temporary forest repairable? Yes, then repair it. Then we have again 3 forests, and see our window has changed from 1, 2, 3 to 2, 3, 4 because we always have the most recent 3 batches. So it's 4th batch, so 4, 3, and 2. That's why. And then again we have 3 forests. We identify which one is the best on this current batch, and then use that forest to classify or predict the unlabeled test data. Then we go to the 5th batch, and then we identify whether this temporary forest is repairable or not. And we see, no, it's possibly not repairable, as I explained before. And then what we do, we again build a new temporary forest. And currently, our most recent batches are 3, 4, 5. So we use these 3 batches of data, as our window size is 3 in this example, toy example. So then we build a temporary forest. And if the active forest is also not repairable, then we realize that after a certain iteration of an active forest being not repairable, we realize that this active forest is not reasonable to continue anymore. It's not reasonable to continue this active forest. So here is a concept we use is sustainable concept drift. So we use 2 concepts called temporary concept drift and sustainable concept drift. Temporary concept drift is, for example, data pattern has changed or underlying distribution has changed due to some special event, for example. And it's not a sustainable concept. It's not a continuing concept drift. It just happened. For example, a city has all on a sudden organizing an Olympic event in that city, and all on a sudden the business pattern, traffic pattern, the vibrancy in the city will have a drift, right? This will change. Lots of tourist visitors are there. The restaurants are busy, but that's not a sustainable concept drift. That just happened because of the Olympic event. On the contrary, on the other hand, imagine that a city is experiencing new investment in the city. For example, Microsoft, IBM, Google, they have opened their big presence in that city. And also, let's assume that 5 new university campuses are being built in that city, opened in that city. So that this is something, a permanent change happening in the city. So we use these two concepts, temporary concept drift and sustainable concept drift, to understand whether this is a temporary concept drift or sustainable concept drift. We actually, although the active forest was not repairable, we did not immediately discard the active forest. We still kept on repairing the active forest as we go, even if it was not repairable. But in case it turns out to be a sustainable concept drift, we also create a temporary forest and we keep updating that temporary forest. But after a certain iteration of an active forest being not repairable, we realize that this is a sustainable concept drift. That's the concept here, right? And then when we realize that, then we actually replace the active forest by the temporary forest. And then in this case, batch number 5, this active forest is actually a copy of the temporary forest. And then when we get batch number 6, we check whether this active forest is repairable. Yes, it is repairable, so just repair it. This is the basic concept. So here we basically actually use three parallel forest: permanent forest, active forest, and temporary forest. And also, as I mentioned, that repairable, we are not repairable. I will explain that in a minute very briefly. We use a theorem called improved separating axis theorem. There is a current existing algorithm called CIRF. It was published in pattern recognition as well in 2018. They used separating axis theorem as a splitting criteria, as their splitting criteria, but we are using improved separating axis theorem as our repairing splitting criteria, trees repair splitting criteria. And here there are some experimental or test results there to see what is the right threshold. Remember, we said that if the number of the percentage of the number of leaves is more than a threshold that requires attention, then this is not repairable. What is that threshold? So we did some experiments to see like what is a reasonable threshold for wherever these user input thresholds are there. And here are some experimental tests as well that shows that having the batch window actually helps in getting better, more accurate forest actually. Remember, we had 3 batches of data all the time. We are carrying the most recent 3 batches of data in case we need to build a temporary forest. So we showed that yes, that actually is useful. Now here is the thing that we used for improve separating this one, improve separating axis theorem. So then a couple of things that possibly you will see in the paper. One is axis aligned minimum bounding box. So it is nothing but a rectangle that that covers a number of data points. These stars are data points, and star is one class and triangle is another class, but these are all data points, and there are 2 variables, AI and AJ. So if I want to encircle or if I want to cover these data points, then the rectangle, the smallest possible rectangle that will cover this is called axis aligned minimum bounding box. So we have 2 axis aligned minimum bounding boxes. So very easily, if I project this to bounding boxes on AI axis or X axis for the variable AI, we can see that there is a clear non-overlap between these 2 bounding boxes. compared to if had I projected them on the y-axis for the variable aj, there would be an overlap. So in this case, our splitting criteria, according to this splitting criteria, we can actually say that the splitting attribute will be ai, and the splitting point will be something that will be that will separate these two bounding boxes. So this is how we generally use this axis aligned minimum bounding boxes as a splitting criteria when we need to repair the trees. So here is an example. I will show you how to repair. So let's say this is our batch 1 data set. And let's say the variables are area of an apartment, number of beds in the apartment, and rent, low or high or normal. And based on that, we can actually use, we can first build a decision tree using, let's say, C4.5 algorithm or whatever, or a random forest using a forest using random forest. So this is one tree of that random forest. Then, according to that that technique that I said that it was published before CIRF technique, according to this technique, we consider that the old data set is one bounding box, and when we get a new batch of the data, then we consider that as a new bounding box. Okay, so like these two bounding boxes, and then we apply these bounding boxes in terms of projecting them onto different axes, and we identify the axis or the variable that can separate them. And in this case, that CRF technique has identified area, and area less than 440. See, all the area in values here is less than 440. So this bounding box goes there. So it remains the same tree, and the new one falls here. But in this case, you can see that the new one has different class values. Like actually the class values have changed. We did not have very high class value in the past. So this class value was not known. So therefore we have a very high, and then out of the 10 records, 6 of them are misclassified. So this is an existing technique, but what we can do is like we could actually build a tree based on entropy based splitting criteria, and then we would get a tree like this. But if we use our algorithm, which is improved, whatever we call it, improved separating axis theorem, then we can get a tree like this. And very briefly, what that improved separating axis theorem is, in this case, let's say we have overlapping minimum bounding boxes, axis aligned minimum bounding boxes. So when we have overlapping axis aligned minimum bounding boxes, we said that according to our theorem 2, that there will be at least, it is possible to have at least 2 sub-bounding boxes which are not overlapping. In this case, these two, let's say. So if we can draw this as a bounding box and this as a bounding box, then they are not overlapping. So then we can have a variable that is the x-axis, and this is the splitting point, and we can easily separate them. After we separate them, what remains is something like this, right? So this is this part of the data are still not classified. Then we identify actually the minimum, the sub axis aligned minimum bounding box that has the minimum number of records, and for that one we use entropy to classify that one. But for the other one, we can easily, so this, when we have this x-axis as the splitting attribute and this point as the splitting point, then we have this two easily divided sets of records, right? Then we can use, then also we can use a horizontal axis at the next layer of the tree to separate this minimum bounding box. And as a result, ultimately, we will be left with this. And then we use, again, a splitting point vertically here on the x-axis to get the clean set of records, and the remaining unclean set of record, I mean the set of records having multiple class values, we just use entropy as usual for classification purpose, for further distribution purpose. So that's the basic idea of this technique. And we then tested this technique on several data sets here, and used our accuracy evaluation, and we can see that ADF, that is this proposed technique with random forest and proposed technique with SIS4, they either random forest or SIS4, one or the other, they generally do very good compared to ADF with Hofting tree approach or existing other incremental learning algorithm like ARF, the CIRF, that the one that uses this axis aligned minimum bounding box as well. All those are bad, and we compared them, and it looks like overall our accuracy was quite high. Yeah, and also in the experimental section, if you read this paper, you will see we have also analyzed the usefulness of the proposed technique ADF for batches with missing values. If we get data with missing values, then what is the impact of that and how we can improve our accuracy in dealing data with missing values. Similarly, data with outliers, then data with class imbalance, then very small number of records if the batch size is too small, and how do we also prevent overfitting for ADF, and how can we handle very big data sets using ADF. So if the data set size is big, like big data problem, then how ADF can be useful there, and also how ADF can be used for data sets with multi-level classes. So that's all from me today. I hope if you enjoyed this this small presentation, and I will stop sharing, and thank you for watching me. Please feel free to download the code. I'm pretty sure that you have lots of questions, and quite a few things possibly were not explained well. So please feel free to read the paper to understand it more, download the code, and I'm pretty sure that you have lots of ideas, and you may find lots of weaknesses and flaws of this paper. Then you have the code, download it and make changes, and test your ideas and see whether you get better result or not. Good luck, and thanks for watching once again. Bye.